Hi, I'm Yao Niu from Super Scientific Software Lab, China University of Petroleum, Beijing. Today, I will introduce our work at PPoPP 22, TileSpGEMM, a tiled algorithm for parallel sparse general matrix multiplication on GPUs. Cooperated with our team members, Zhengyang Lu, Haonan Ji, Shuhui Song, Zhou Jing, and Professor Weifeng Liu. Okay, let's take a brief introduction of SPGEMM. SPGEMM is short for General Sparse Matrix Multiplication, and it multiplies two sparse matrices A and B and gives a resulting sparse matrix C. And the figure below shows a very simple example of SPGEMM. So as we can see, 4x4 sparse matrix A multiplies a 4x4 sparse matrix B, and the 4x4 resulting sparse matrix C is to be computed. The classic SPGEMM method proposed by Gustafsson is a row method. That is, in the figure, the element 1 in the first column is used to scale the first row of B, and the intermediate product is inserted to the temporary space. And then the element 2 in the third column is used to scale the third row of B, and the intermediate product is added to the third column in the temporary space. And then the first row of C is completed. Repeat this procedure, and finally we can get the resulting sparse matrix C of 8 non-zeros. And we can find that calculating each row of C is independent with each other. So it is very easy to be parallelized. Why we say that SPGEMM is very important, it is because the SPGEMM is a very key kernel in Sparse Plus, and it has a wide range of applications. For example, in the sparse linear solvers, such as algebraic multigrid methods, and the graph processing unit, such as breadth first search, and it can also be applied to machine learning, such as deep neural network. Despite lots of researches and despite lots of efforts, SPGEMM still have 3 performance issues that the row style method inherently has, and that motivates us to design a totally different data structure. And on top of this, we propose our tiled algorithms called TileSpGEMM, and then we evaluate our TileSpGEMM and compare with other SPGEMM methods. So let's talk about some performance issues first. So the first performance issue is about load imbalance, which is the traditional performance issue on parallel computing. So we also use this simple exam to illustrate it. So when we multiply C and B, we first record the number of intermediate products of rows of C. So the number, the first row is A3, and the second row of 2 plus 2 plus 2 equals 6, and the third row 0, and the first row 2. And it is so obvious that the number of intermediate product of rows is very imbalanced. So when we deal with the very large scale matrices, the web-based, for example, it is a very classic power law matrix. And load imbalance issue is more obvious. So in this case, it is so hard to saturate massively parallel GPUs when a small number of long rows dominate runtime in the rural style. And the second performance issue is about the size of C. We all know that as we mentioned before, the resulting C is sparse. So this is why the SPGEMM is the most complicated kernel in Sparse Plus. In order to complete the computation, we first have to do the symbolic SPGEMM to get the number of non-zeros of C. And after that, we can malloc space for C, and then we do the numeric SPGEMM. So in this case, actually, we will do twice real SPGEMM in the process. So the size of C is unknown in advance and requires a space for storing a possibly large amount of intermediate product. So it is very hard to allocate a proper size at runtime. And the third one is about the sparse accumulator selection. In recent years, some various sparse accumulators have emerged such as heap method, merge method, ESA method, and hash table method. However, the rural method inserts non-zeros to random positions in the rows of C of unpredictable sparsity. So it is so hard to design a sparse accumulator to efficiently accumulate new entries. So considering the inherent performance issues, we decide to design a totally different data structure and named tile data structure. Giving 16 by 16 sparse matrices, we no longer store it as a rural style. On the contrary, we store it as a number of sparse tiles of the same size and use two levels data structure to represent it. And the higher level stores the information of tiles, and we use three arrays to store it. And firstly, we record the tile column index and the number of non-zeros of each tiles, and then to be more convenient for future computation, we make a prefix sum with of the NZ array, and the tile NZ array is generated to store the memory offset of the number of non-zeros of each tiles. And besides, we use the tile pointer array to store the memory offset of the number of tiles in each tile row. And the lower level stores the specific information of each non-zero. So here we take the orange tiles as an example. In our lower level data structure, we actually use a combination of CSR and CO format to store a sparse tile, that is the value array, column index and row index array, and the row pointer array. And plus, we use a mask array to store the bit mask of a sparse tile. Specifically, we mark 1 in the column index, corresponding column index positions, and mark 0 otherwise. So that's this figure shows the entire tile data structure for a given 16 by 16 sparse matrix. And as we can see in the figure, the tile size is 4 by 4, and in our real experiment, the tile we set the tile size of 16 by 16, and they have 3 major reasons. And the first reason is we want to use 8-bit unsigned char for storing pointers. And the second ones, we use 8-bit unsigned char for storing row and column indices on one position. And the third one is we want to use 6-bit unsigned char for bit masks. And on top of this, our tiled data structure, we propose our new SPGEMM algorithm, TileSpGEMM, and it can be divided into 3 steps. And this figure shows the whole process of 3 steps. And step 1 is find the possibly non-empty tiles in C. And after this step, we can get a time pointer C and time column index C array of the higher level data structure of C. And step 2 is to determine the number of non-zeros and the row pointer array of each tile in C. And after that, the tile NZC and mask C is obtained. We can allocate the resulting matrix. And step 3 is computing the C and specifically calculating the row and column indices and values of the non-zeros in each tile of C. And after that, the row index C, column index C, and value C are all obtained. So let's start with the step 1. In this step, we create a new matrix A prime, and according to the original matrix A, and the number of row of A prime is the number of tile row of A, and the number of non-zeros of A prime is the number of non-empty tiles of A. So we can observe that the standard CSR format of the A prime is totally equals to the higher level or data structure of the original matrix A. So in this step, we directly run a SPGEMM to multiply the high level tile structure of the 2 input matrix A and B. And then after getting the resulting matrix C prime, the number of non-zero in the resulting matrix C prime is the number of non-empty tiles in C. And then the number of non-empty tiles is obtained. In this step, we directly use the directly called the Sparse library because the scale of the high level data tile structure is relatively small. And there are 2 main reasons. First off, the Sparse library is use very simple interface to use, and more importantly, the Sparse has better performance on small cases. And then after step 1, we now want to calculate each tile of the number of non-zeros of each tile of C. And we must find the corresponding tile row and tile column in A and B. So it is obvious that the empty tile in tile row and tile column in A and B shouldn't be involved in the computation for the performance consideration. So there are 2 questions that need to be answered. The first is how to find the tile pairs in A and B that should be multiplied. And the second is how to generate the row pointer array and the number of non-zeros of each tile of C. And let's answer the first questions at first. So in our paper, we use the binary search to find the tile path. And as we can see, the tile row index B and tile column index A are listed on the right of the screen. And after comparing their lengths, we decided to binary search tile row index B in tile column index A. The elements, all the elements are searched in tile column index A 1 by 1. for example, the search one and after the first search and return the positions, and the same operation as the element 3. Okay, return the position 2 and record in the position arrays. And then let's answer the second question, and that is how to get the row pointer of each tile of C. So normally, this step is to do a symbolic SPGEMM. However, in our paper, we use bit mask rather than the original tiles of B of each tile to reduce memory transfer cost of repeatedly loading structure information of tiles in B. And then we perform atomic OR operation on all the extracted line mask on the scratch pad memory. And finally, the mask of C12 is generated. And after step 2, we have known the number of non-zeros and the row pointer of each tiles, and then we can calculate the row index, the column index, and values of each non-zeros. In this step, we design an adaptive method for selecting sparse or dense accumulator in on-chip memory. And we set a threshold that is the 75% of the tile size, and in the figure, and as we can see, the value is equal to 12. So when the number of non-zero is greater than 12, they will choose a dense accumulator. Otherwise, they will choose the sparse accumulator. And let's take the computation of C12 as an example. So as we can see, the number of non-zeros of C12 is 12. So we first work on a dense form matrix and then save the result into its sparse form. And in our dense accumulator, we do not need to allocate a very large temporary space. And as for the computation of C32, this tile is relatively sparse. Then a sparse accumulator working on sparse tile is selected. And so in our sparse accumulator, the mask generated in the step 2 is used to generate the column index. And then the atomic add operation is operated to compute the value. And as we can see in our sparse accumulator, we do not allocate a very large temporary sparse either. And that's all our advantage. We evaluate our algorithms on the NVIDIA RTX 3060 and 3090 GPUs of Ampere architecture, and compare our algorithms with TileSpGEMM, PPoPP, N-Sparse, SPEC, and T-Sparse. As for our benchmark, we use 142 sparse square matrices, requiring no less than 1 billion floating point operations when performing A square and AA transpose. We also select 12 classic matrices in much sparse matrix research. As we can see on the left, some matrices like Kant, web-based are commonly used. And firstly, we compare our algorithms with TileSpGEMM, PPoPP, N-Sparse, and SPEC when performing double precision A square and AA transpose. So as we can see, our SPGEMM and SPEC can finish all the matrices in our dataset, while the other 3 methods can only complete a part of our dataset. And then the figure shows that our TileSpGEMM run faster than other 4 methods on most matrices, and then we can get and we can get on average 1.77, 4.73, 1.45, and 1.16 geometric mean speed up than other methods. And the sub figures on the bottom shows the scalability comparison. And as we can see, our method is the scalability of our method is greater than Sparse, but a little worse than Sparse and SPEC. This is because some matrices using our method have more arrays to allocate than GPUs and takes longer time to memory allocation. And to conduct a more detailed analysis, we listed 18 representative matrices and listed and plot their performance comparison. And as we can see, the when calculating the matrices that other method cannot complete successfully, our method shows much better advantage. And this is because our method naturally avoids the allocation of temporary products. And as for the classic power law matrix web base, our method is also get more than 12 G-flops when performing A square and about 31 G-flops when performing A transpose, which is much better than other methods. We also plot the runtime peak space cost, and from the figure, we can see that in most matrices, TileSpGEMM use less space than other methods and finishes earlier. However, for some matrices such as the COP20K, our methods have to allocate a large number of sparse tiles for pointer and bit mask, and thus may use longer time to allocate and compute. And we also plot the space cost, and we compare the space cost of our tile data structure with the standard CSR format and CSP format proposed by ADAM. And as we can see, our tiled data structure takes less space than CSR, but use more space than CSP. But we think this space cost is acceptable because we bring the performance efficiency. And the format conversion time is also plotted in the figure. As we can see, this cost would be acceptable because the matrix is already stored in the tiled format, and which is very beneficial to some applications such as AMG, who use the output matrices from an SPGEMM as the input of another SPGEMM in the next round. We also compare our algorithm with T-Sparse, which is a relatively new SPGEMM work designed for using half precision and dense tensor cores on modern GPUs. And we tested 16 matrices listed on the T-Sparse paper and compared the performance. So our TileSpGEMM outperforms T-Sparse on all of the 16 matrices. So in the final, make a conclusion, and we demonstrated 3 performance issues and that the RoRo method have, and then we decided to design a totally different format called tile and data structure. And according to the data structure, we propose our 3-step TileSpGEMM. And the experimental data shows that our TileSpGEMM outperforms other latest SPGEMM method. And that's all. Thank you very much for your time.